Hi everyone, welcome back to my channel. My name is Sunny, and today we are going to discuss how AI agents actually work. So let's start with what is agentic AI and how AI agents actually work. What if you could give an AI system a business objective and instead of simply telling you what to do, it could actually figure out how to accomplish it? It could analyze the problem, formulate a plan, call the appropriate tools, inspect the results, recover from failures, and continue working until the objective is achieved. That is the promise of agentic AI. So, in this video, we are going beyond the buzzwords. We will understand what an AI agent actually is and how the agentic loop works, how models, memories, tools, and planning fit together, how multi-agent system operate, and what a production grade architecture look like, because the future of AI isn't simply about generating better answers, it is about building systems that can pursue meaningful goals. Let's move to second slide. So the shift from answers to outcome. For years, our interaction with software has been fundamentally deterministic. We tell the system what to do, and the system follows a predefined path. Generative AI changed that interaction. We can now describe what we want in natural language, and a model can generate an answer. But agentic system takes another step. Instead of treating the interaction as a question and answer exchange, the system can treat the request as an objective. It can decide what information it needs, determine which actions are appropriate, use external tools, inspect the results, and continue iterating. That is the shift from answers to outcome. Now, the important distinction is this: a chatbot primarily responds, and agent is designed to execute. So, now let's discuss what exactly is an AI agent. So, at a high level, an agent is a system that can pursue a goal with a degree of independence while operating within defined instructions and boundaries. There are several important ingredients. First, we have the model, the reasoning, and decision making engine. Second, we have tools. This allows the system to retrieve information or take actions in external systems. Third, we have instructions and guardrails that define what the agent is allowed to do and how it should behave. And finally, we have orchestration, the mechanism that manages the execution loop. This distinction matters because simply placing an LLM inside a chat interface does not automatically create an agent. The model needs to participate in controlling the workflow. So now let's understand what is agentic loop. The defining characteristics of an agent is not simply intelligence, it is the ability to operate within a continuous decision loop. The process begins with a goal, the agent intercepts the current state, reasons about what need to happen, formulate a plan, and take an action through one or more tools. Then comes the critical step, that is observation. The agent receives the results of its action and evaluates whether the objective has actually been achieved. If it has not, the agent can revise its plan, select another tool, and continue the loop. This closed loop behavior is what transforms an LLM from a conversational interface into an agentic system. In production system, the loop is also bounded by exit conditions, permissions, safety rules, buzzers, and sometimes human approval. Now look for the another slide. So what is inside an AI agent? If we open the architecture of an agent, we can identify several recurring capabilities. The LLM provides reasoning, memory provides context and continuity, tools provide access to the outside world, planning allows the agent to decompose a complex objective into smaller decisions, and guardrails establish the boundaries within which the system can operate. So none of these components should be considered independently. A powerful model without tools may be unable to act. Tools without good reasoning may be used incorrectly, and memory without access control can create security risks. The real engineering challenge is therefore not simply selecting a model, it is designing the complete system around the world. So let's move to sixth slide. The brain, the LLM. The language model is often described as the brain of the agent, and the analogy is useful provided we remember that the brain is only one part of the complete system. The model interprets instructions and context, reasons about possible action, and selects what it believes should happen next. Important thing is the model may receive much more than the user's original message. It can reason over system instructions, conversation history, retrieve knowledge, previous tool results, and the available tool definition. The agent runtime that converts that reasoning into actual execution. So when we say an agent is intelligent, we are really describing an interaction between the model and the surrounding execution environment. So now let's discuss about memory giving agents. So intelligence without context is fragile. An agent need to understand what is happening now, what has already happened, and in sometimes what it has learned from previous interaction. Short term context can include the current conversation, the active task, and recent tool results. Longer term memory can preserve preferences, corrections, domain knowledge, and other information that should remain useful across sessions. So, but memory is not simply a storage problem, it is also a retrieval and governance problem. The agent must retrieve the right context at the right moment, respect permissions, and avoid carrying irrelevant or outdated information into a decision. In other words, context is one of the foundation of a reliable agent behavior. So now let's discuss about the tools connecting AI to the real world. A model can reason without action. A tool allows the system to actually perform that action. So this is where agentic AI becomes significantly more powerful. A search tool can retrieve information, a database tool can query business data, and API can interact with enterprise systems. A code execution environment can run and validate a software. A computer use capability can operate a digital interface. We can broadly think about tools in two categories: data tools and action tools. Data tools help the agent understand the environment, action tool allows the agent to change the environment. The agent therefore becomes the bridge between intelligence and execution. Now planning how we can turn goals into a work. So complex goals rarely map to a single action. Suppose we ask an agent to prepare an enterprise architecture recommendation in per it may first need to gather context, then inspect constraints, then compare architectural options, then evaluate trades-off, and finally produce a recommendation. The important point is that these immediate steps do not necessarily have to be explicitly written by a human as a rigid workflow. The agent can reason about the objective and determine an appropriate sequence of actions subject to the instructions and constraints we provide. So this is one of the major differences between deterministic automation and agentic execution. The system is not merely following a fixed script; it is making a bounded decision about how to accomplish the objective. So now let's discuss about from prompt to action. So what actually it means? So in this, we are just going to put the pieces together. A user starts with a request. The agent first intercepts the objective. It then determines what need to happen. select an appropriate plan, and choose the tools required to execute that plan. The tool may return information, modify a system, or produce an immediate result. The agent then evaluates what happened. If the result is sufficient, the workflow can finish. If not, the agent can continue with another step or revise its approach. Notice what has changed. The fundamental unit is no longer the prompt, it is the goal. The prompt is simply one way of expressing the goal to the system. So now single agent versus multi-agent system. So not every agentic application requires multiple agents. A single agent with a strong model, clear instruction, and a well-designed set of tools can handle a surprisingly broad range of workflows. So, as complexity increases, however, we may choose to distribute responsibility, and one agent might specialize in research, another might focus on coding, a third might review the result. A manager agent can coordinate these specialists, or agents can hand work to one another. This introduces a new architectural dimension or gestation, but multi-agent should not automatically mean better. Every additional agent increases coordination, context management, evaluation, and operational complexity. Good architecture uses multiple agents when specialization generally improve the system. So now let's understand with the example the AI software engineering agent. So imagine that instead of asking an AI, write me a React component, we give it an engineering objective. The agent can inspect the repository, understand the architecture, locate the relevant modules, formulate a plan, modify the code, run tests, inspect failures, and iterate. This is a fundamentally different interactions. Traditional code generation focuses on producing a piece of code, and engineering agent is responsible for progressing uh, towards an outcome. That distinction, code generation versus engineering execution, is one of the most important ways to understand the emerging role of agents in software development. So let's move to another slide. So this is an example of an enterprise's AI agent. The enterprise becomes even more interesting because business processes rarely live inside a single application. A customer request may require information from a CRM, internal documentation, and ERP system, a ticketing platform, and a communication tools. An agent can potentially coordinate across these boundaries. So it can retrieve the relevant information, reason about the situation, decide what action is appropriate, and then invoke the corresponding system. Of course, this capability must be governed carefully. Enterprises agents need identity, permissions, auditability, observability, approval mechanism, and clear boundaries. The objective is not uncontrolled autonomy. The objective is controlled execution at scale. So let's discuss about production architecture, how it should be. So a production grade agent is much more than a powerful model. At the top, we have the user or an event that indicates the workflow. The orchestration layer manages the agent loop. The model and memory provides reasoning and context. Tools in data connect the agent to the real environment, and around everything we need guardrails and observability, security, permissions, uh, tracing, evaluation, cost controls, and human approval are not optional decorations. They are part of the architecture. So this is why building reliable agents is fundamentally a system engineering problem, not merely a prompt engineering exercise. So let's discuss about the agentic AI technology stack. So, when evaluating agentic AI technology, I recommend thinking in layers. At the application layer, we have the user experience. Below that sits orchestration, the logic that manages the agent loop and workflow. Then comes intelligence, the model that perform reasoning. context system provides memory, retrieval, and knowledge. Capability system provides APIs, databases, browser, code execution, and other tools. Finally, infrastructure provides the runtime, security, scaling, and observability. Framework will change, model will change, vendors will change. But these architecture layers are useful because they help us reason about the system independently of a single technology. So now hard problem. Agentic AI introduces a new class of engineering challenges. First, hallucination and incorrect assumption. An agent can make a wrong decision and then execute that decision. Second, a security. A system capable of taking action must have carefully controlled permissions. The third is reliability. Agentic workflows can follow different paths depending on context, making testing more complex. Fourth, cost long running workflows can consume significant compute and tool resources. And finally, human control. The question is not simply can the agent do this? The better question is under what condition should the agent be allowed to do this autonomously. The goal is not unrestricted autonomy, it is useful autonomy inside well defined boundaries. So, where agentic AI is going, so we are moving through an interesting progression. First come copilots that suggest direction, then assistants that could collaborate with us. Now we are building agents capable of executing workflows. And the next step is increasingly coordinated agents networks where specialized systems work together across longer running tasks. This does not mean humans disappear from the loop. In many high value environments, human will continue to define objectives, establish policies, approve sensitive decisions, and provide judgment. The role of software is changing from something that simply executes explicit instructions towards something that can participate in the execution of intent. So, this is the last slide in the PPT, the big data. So, let me leave you with one idea. Generative AI taught mechanism how to create. Agentic AI is teaching mechanics how to accomplish. That distinction may sound subtle, but architecturally it is profound. So we are moving from systems that respond to individual interactions toward systems that can interpret objectives, make boundary decisions, use tools, interact with their environment, and execute multi-step workflows. And that raises a much bigger question for software engineers and technology leaders. If software can increasingly decide how to accomplish a goal, what does software engineering look like when human define the objectives and intelligent system execute the work? That is the conversation we are only beginning to have. And that is why agentic AI is not simply another AI trend. It represents a fundamental shift in how we think about software. So this is for today. See you in next video. Thank you.